Hello Year 10 and welcome to another week of remote learning. We move on to a new topic this week and indeed to a new module looking at probability and statistics. The reasoning for this is multifaceted, but predominantly from your perspective I think this module is better suited to remote learning, and also the questions are easier to answer on Dr. Frost Maths than having to sketch out a lot of graphs in a complex manner. So, just like last week, I'm going to go through a few questions that are relevant to the reading you have already done. If you have not yet read through the CGP revision guide, pause this video, go and do that, and then return to me. So question 1 we look at: Tamara has a bag containing n balls, each of which is either purple, white or black. The probabilities of a randomly selected ball being each colour are shown in the table, and you can see that they're given in terms of some unknown variable x. Find the value of x, and then the probability that a randomly selected ball is black. As soon as you see a question like this, where you don't know the probabilities, but they're given to you as some sort of expression, it should be leaping out to you that you're going to use the idea that probabilities sum to 100%. That is, in this case, the probability of either getting a purple or a white or a black ball is 100%, or is equal to 1. When I reach out a ball, those are my only three options. That's what it tells me in the question. So I know that 11x plus 15x plus 24x is equal to 1. So 11x plus 15x is 26x plus 24x is 50x is equal to 1, and so x is equal to 0.02, or 1/50th. That's part A done. Part B wants the probability that a randomly selected ball is black. So that's 24 times x, 24 times 0.02, which is 0.48. And there's the question sorted. The next example we move on to look at. A biased dice is rolled 40 times, a 6 came up 14 times. Calculate the relative frequency that a 6 was rolled. Relative frequency pertains to experimental probabilities. You're probably more familiar with theoretical probabilities. That is, that if I, for example, toss a coin 100 times, my theoretical probability of getting a head is 50%. But actually, it's not guaranteed that I'm going to get 50 heads when I do that tossing 100 times. So when we're dealing with experimental probabilities, we look at what we actually have generated from our data. Now, if we have a larger data set, let's say I toss the coin 1,000 times instead, I'm likely to get closer to my theoretical probability. But crucially, my experimental probability always accounts for some random error, and therefore we can never guarantee, no matter how many times I toss the coin, that we're going to get exactly 50% heads. So with all that, a biased dice is rolled 40 times, a 6 comes up 14 times. Relative frequency is very simply 14 out of 40. A frequency is how many times does that happen. 14 times out of 40, which is 7 out of 20, or 0.35. The same dice is rolled another 60 times. From this, a 6 came up 24 times. Calculate the relative frequency. Same idea, 24 out of 60. Which I can cancel nice and easily with 12 as my factor, 2/5, which is 0.4. Use the data from A and B to make the best estimate of rolling a 6 with the dice. You'll note that I am expecting my probability... Oh, it's a biased dice, so I don't really know what to expect actually, but this is certainly higher than if it wasn't biased. I note that I've rolled 40 times and then another 60, so in total I've rolled 100 times. The 6 came up 14 times and another 24 times. So in total it came up 38 times, and therefore the best estimate of my probability is 0.38. So we're drawing there a distinction between my relative frequency, their absolute values, and my probability, which is just an estimate from what I've collected. It's entirely possible that if I rolled the dice another 100 times, a 6 would come up 30 times, or 40 times, or even 100 times, although that's very unlikely given the data we have in front of us. And so we're just estimating our probability from a finite number of attempts. Our third question looks at sample space diagrams. This is a way of thinking about probability. A sample space diagram showing all the possible combinations of scores after throwing a standard dice and spinning this spinner. So a standard dice, I know, can have answers from 1 to 6. And my spinner, 1, 2, 3, 4, 5. And crucially here, from my spinner, equal probability, and from my dice, equal probability. So, you could of course do this much neater than I am about to. Now the convention would be to write my combinations as, for example, for this box here, 1, 1, and then this box here, 1, 2, and so on. So brackets around our total combinations. Because I know where the question's going, I'm not going to do that, but that would be a useful thing. So find the probability of throwing a 1 on the dice and spinning a 5 on the spinner. 1 on the dice, let's label these so we don't get confused. Dice and spinner, 1 on the dice, and a 5 on the spinner. There's only one possibility there, so that's 1 out of a total of, and then we have 5 times 6, 1 out of 30 is my probability. That's the probability of throwing a 1 on the dice and a 5 on the spinner. The probability of getting a total score of 10, this is why I haven't written everything in here, because it helps me to think about this. A total score of 10, well, I can rule this whole column out because I'm getting up to 7, whole column up to 8, whole column up to 9, there's a 10 here and a 10 here. So that's 2 out of 30, or 1/15th as my probability. Probability of getting a total score of at least 9. So these two shaded regions still count in this case, because they're both 10. 5 plus 6 is 11. 5 plus 4 is 9. 4 plus 5 is 9. 3 plus 6 is 9. And then if I test any of these values, I've got 8, 8, 8, 8. So these are all of my values that give me a score of at least 9. That is 6 out of 30, or 1/5 as my probability. My final example question looks at counting principles. A car wash offers different levels of cleaning for different parts of a car. 3 different levels of cleaning for the outside, 5 for the inside, 2 for the underneath. A customer wants the outside, inside, and underneath of their car washed. How many options in total? So we're looking here, when we're talking about counting principles, at our AND rule, or our product rule for counting, and our OR rule, or our addition rule for counting. The customer wants the outside and the inside and the underneath. So there are 3 ways to do the outside, and 5 ways to do the inside, and 2 ways to do the underneath. So in total, there are 3 times 5, 15 times 2. There are 30 ways to do the outside, inside, and underneath. Another customer wants only 2 of the 3 parts washed. Shows she can choose from 31 of the possible outcomes. So, if she only wants 2, she could have the outside and the inside, 3 ways and 5 ways, or she could have the outside and the underneath, 3 ways and 2 ways, or, and you'll notice I'm adding these or possibilities, or she could have the inside 5 ways and the underneath 2 ways. And so we have in total 15 plus 6 plus 10, which is 31 ways, as was required in the question. Hopefully that's elucidated some of the harder concepts that you're being asked to self-study here. Your teacher will cover tree diagrams and other ways of finding probability in their live lesson this week. Other than that, good luck and have a good and productive week.